Look at these two vehicles. On the left, a traditional horse-drawn carriage. On the right, a motorized car from the early 20th century. Structurally, they look nearly identical. They share the same seating, the same basic frame, and the same wooden wheels. The only real difference is that one has a horse and the other has an engine. For a while, calling those first cars horseless carriages was an accurate description, but eventually that label stopped working. There wasn't one single flashy moment where the car became an entirely different machine. Instead, there was an accumulation of quiet, invisible upgrades: better brakes, new suspension, electrical systems. We have been doing the exact same thing with artificial intelligence. For years, we've described language models as sophisticated autocomplete engines, systems built simply to predict the next word based on the text you just typed. That metaphor was useful in the beginning because it was simple. But the underlying architecture has evolved past the joke. Calling these models autocomplete completely misses the physical reality of what is actually happening under the hood today. If you've ever had a really long conversation with a language model, you've probably noticed a specific kind of breakdown. The system starts out sharp, tracking every detail, but eventually it begins to lose the thread. It drops important nuances, contradicts rules you established an hour ago, and the rich context of your chat flattens out. When we see this happen, our instinct is to treat it like a human failing. We assume the model has reached the limit of its reasoning capacity, or we write it off as a cognitive hallucination. But the model hasn't suddenly become less capable. It has simply run out of the physical memory required to keep your past conversation alive. The system doesn't forget because it doesn't know. It forgets because remembering is incredibly expensive. It is a strict physical bottleneck. The computational cost of maintaining that active context hits a ceiling, and the model can no longer sustain the weight of the interaction. To understand this cost, we have to look at a hidden piece of architecture called the KV cache. This is the physical space where your active context lives. Every word, or token, is converted into mathematical vectors, keys, and values, and stored here while the model formulates its response. The problem is that this cache grows constantly. With every single token generated or read, a new block of data is added, creating a massive drain on hardware memory. Very quickly, the system faces a brutal choice. It either pays an exorbitant price in memory and processing power to hold on to everything, or it starts dropping pieces of your past, sacrificing coherence to save space. This is where a new piece of engineering called TurboQuant comes in. It is an algorithmic technique designed specifically to compress this massive cache, shrinking the physical memory footprint without destroying the semantic direction of your conversation. Now, TurboQuant is essentially a plumbing fix. By aggressively slashing the economic cost of storing data, it radically expands the limit of what the system can hold at once. Here is how it actually works. First, TurboQuant takes the high-dimensional data vectors in the cache and applies a mathematical rotation. This rotation redistributes the information. It prevents any single dimension from carrying too much weight, making the data entirely uniform and much easier to compress. Next comes the actual quantization. The system takes these high-precision numbers and aggressively chops them down, representing each dimension with just a handful of bits. Compressing data this hard usually introduces distortion. So TurboQuant applies a final correction, a one-bit transform, that realigns these tiny fragments to preserve the exact geometric relationships of the original vectors. In language models, meaning is not stored in isolated words. It is stored in the geometric relationships between vectors. Because these highly compressed fragments still point in almost the exact same direction in mathematical space, the original meaning survives. The system can now pack vastly more context into a fraction of the memory. It takes a massive hardware limitation and bypasses it entirely through geometry. When you remove that memory bottleneck, the behavior of the model changes. It can now operate with a high density of the past readily available at all times. This upgrade doesn't magically generate new intelligence. What it does is prevent the intelligence that is already there from dissipating as the clock ticks. Conversations gain real permanence. The model holds on to its internal logic in the rules you established early on, because the context is structurally sustained instead of being thrown out to save space. Context is the absolute structural condition for coherence. TurboQuant makes that long-term coherence economically viable. This is exactly like those early automotive upgrades. Nobody held a parade for the invention of better suspension or optimized electrical wiring. You won't see TurboQuant advertised on a billboard. Yet it is the silent, essential infrastructure underwriting the entire next generation of language models. We are moving from a system that guesses the next word to a system capable of sustaining an unbroken train of thought over incredibly long interactions. As continuity expands, calling these models autocomplete is like looking at a high-performance engine and seeing nothing but a carriage missing its horse.